everyone, welcome to the channel Exam Ignite. Today I am continuing the part 2 of the module 2, that is vector operator topic. Part 1 is already done. Please refer the description box for the part 1 link. So here vector operator, it is denoted by nebula. So nebula is equal to dou by dou x ax cap plus dou by ay cap plus dou by dou z az cap. A vector is equal to ax into ax cap plus ay into ay cap plus az into az cap. Here, capital A's are the constant and others are the small a's are the unit vector. Multiply both of them, you will get nebula into a vector. After doing that, differentiate that ax cap into ax cap is dot product is 1. Similarly, ay cap into ay cap dot product is 1. That gets multiplied. Now you have to find the gradient of a vector, that is you got nebula dot a vector has the given formula. Now curl of a vector is found out by the nebula across a vector. You have to do the cross product. So ax cap in ax cap, ay cap, az cap, then dou by dou x, dou by dou y, dou by dou z, ax, ay, az. If you find the determinant of this, then you will get the curl of that a vector. Next topic is point form of the Gauss law, that is also called as Maxwell's first equation. Surface integral of d vector dot ds is equal to delta q, which is if you take the delta, divide the both the equations by delta v, then you will get limit delta v tends to 0 and the integral of d vector dot ds vector divided by delta v, that is limit delta v tends to 0, that is delta q by delta v, which is rho v. Next, nebula dot d vector is equal to rho v. Divergence of d vector is equal to rho v. The divergence of electric displacement density in the medium at a point can be infinitely small and is equal to the charge per unit volume at the same point. Now the Gauss divergence theorem. The integral of the normal component of the flux density over any closed surface in an electric field is equal to the volume integral of the divergence of the flux throughout the space enclosed by the surface. This is the statement, that is surface integral of d vector dot ds vector is equal to volume integral of nebula dot d vector dot dv. So rho v is equal to limit delta v tends to 0. Now delta q divided by delta v is equal to small dq by dv. Now dq is equal to rho v into dv. We know that. So q is equal to what? Integration of all the small dq's, that is volume integral of rho v into dv. We know that nebula dot d vector is equal to rho v. Q, substitute that in this place, in the rho v place. After substituting, we know that volume integral of d vector dot ds vector is equal to q. So replace the q with that. So hence we will get the Gauss divergence theorem equation. What is the statement for the Gauss law in point form? That is the previous one is the divergence of the electric displacement density in a medium at a point and infinitely small volume is equal to the charge by unit volume at that same point. Now we are having three main derivations, that is nebula square v in the different coordinate system, that is Cartesian. We have this a very important formula. This is what needed to solve your problems in this module, which is an expected question in the exam. The Cartesian, you have nebula square v is equal to dou square v divided by dou x square plus dou square v divided by dou y square plus dou square v divided by dou z square. For the cylindrical of the coordinates r comma psi comma z, you get nebula square v is equal to 1 by r dou by dou r of r into dou v by dou r plus 1 by r square dou square v divided by dou phi square plus dou square v divided by dou z square. Spherical of the coordinates r comma theta comma phi, nebula square v is equal to 1 by r square dou by dou r of r square dou v by dou r plus 1 by r square sin theta dou by dou theta of sin theta dou v by dou theta plus 1 by r square sin square theta dou square v by dou phi square. Next topic is potential difference. The potential difference between 2 points in an electric field is what the amount of work done against the field in moving a unit positive charge from one point to another. Therefore, the work done from A to B will be what? VB minus V. That is the difference. Energy expended in a moving point charge. A derivation where you consider a point Q at point A in a uniform electric field where F force is equal to energy. So F is equal to Q into E. Consider that as a first equation. Charge is moved along the A to B, inclined to an angle of theta. You can observe it here. Now the force acting on this charge is what? It is equal to F cos theta of 180 minus theta, because you have to consider here. So 180 minus theta. What is F? F is equal to Q into E. And cos of 180 minus theta is minus cos theta. Then work done and moving a charge from A to B will be work done into distance from the movement. So minus QE cos theta into delta L. What is the amount of length, or is the length moved? Now as the dot product, W is equal to minus QE into delta L. For the differential element, we can say dW is equal to minus QE vector dot dl vector. Now energy integral, line integral of the electric field and potential difference. This is a very important derivation. So consider a charge Q at a point A in an electric field. To find the work done from moving a charge from A to B in an arbitrary path. So first we will consider an equation F is equal to Q into E as equation 1. We know that the delta W in moving a charge through a small length dl from A to A dash is what? W is equal to minus Q of E vector dot dl vector, right? As we learnt in the previous derivation. That is considered as equation 2. Imagine the total path is divided into number of segments. That is, see here. This is the delta L1. This is delta L2, delta L3 similarly. So over a field lines of what? Electric field 1, electric field 2, etc. So total work done will be summation of all those small work done. That is minus Q into work done of the first one, that is E1 my E1 vector dot delta L1 vector plus E2 vector into delta L1 vector L2 vector. Similarly it goes on. So what we can write, minus Q into summation of I, that is EI vector dot delta Li vector. If the length is infinitely small, that is for the delta L, if we consider very small length of dl, then work done will be replace delta L as dl. We get the equation 3. If VA and VB are the potentials, then we can say W is replaced by VA minus VB. In an uniform, this is not for an uniform electric field. Now, if we consider for a uniform electric field, then W is equal to what? Minus QE. From where A to B, it has to be integrated to find the work done. Then dl vector, that is minus QE vector dot LA from limits from A to B. So VB minus VA is equal to minus QE vector dot L vector AB. What is electric current? Next topic. The rate of flow of charge, that is the amount of charge flow across a given cross section of conductor per unit time, is called as an electric current. Delta Q will be the amount of charge that flows across the given cross section. Delta T will be the time in the seconds. So I current is given as delta Q divided by delta T. Steady current if the rate of flow of charges remains constant with time. Then instantaneous current is the flow of charge that is subject to the continuous variation with the time. That is I is equal to delta Q by delta T. For delta T tends to 0, then the smallest current will be dQ by dt. Next topic is current density. It is defined as the current per unit area of cross section of an imaginary plane held normal to the direction of current in the current carrying conductor. So consider, we have a derivation here. Consider a conductor. It is having a current I. Cross-sectional area of the conductor normal to the direction of the current. Delta S in the small area at the point P, and delta I is a part of the current that is flowing through the delta S. Now then the magnitude of J will be what? It will be delta I by delta S, where S tends to 0, and di, that is a di by ds. This will be my first equation. Now the direction of J vector is same as that of the I. So di is equal to J vector dot ds vector. Total current will be I is equal to integration of small currents, that is di, which is equal to integration of S into J vector dot ds vector. Equation of continuity, this is an important derivation. Here consider a closed surface. If there is any charge flowing through the surface, then the small area, consider small area of ds. That ds will be what? J vector, that is current density dot ds vector. Now total charge overflow from the entire closed surface will be what? Integral of J vector dot ds vector total, adding all those small ds. Now consider a volume. that is dV, inside the surface where charge density is rho v. The charge within the closed surface will be what? Integration of v, rho v dV. When the charge flow out of the surface, that is time will be reduction of the charge within the surface, that is minus dou by dou t, integration of v into rho v into dV. Now finally integration surface integration of j vector dot ds vector is equal to minus dou by dou t, integration of volume integral, that is rho v by dV, rho v into dV. This will be my integral form of the equation of continuity. But according to the divergence theorem, we know that rho v into nebula a vector dot dv is equal to surface integral of a vector dot ds vector. So volume integral of nebula dot js vector dv is equal to integral of j vector dot ds. This will be my equation number 9. So from 9 and 8, what we can write is volume integral of nebula j vector dot dv is equal to minus dou by dou t volume integral of rho v into dv. So differentiating on both the sides, what do we get? The integration is removed. So nebula dot j vector is equal to minus dou into rho v by dou t. This is what our equation of continuity. So this completes all the derivations of the second module. Part 2 video is also completed. I'll start with the module 3. Stay updated and do subscribe my channel for the next upcoming videos. Thank you.